In Lab 3 of Physics 2211, we simulated a black hole using code. The purpose of this lab is to use a computational model to simulate the interaction between a star and black hole, which will allow us to determine the mass of the black hole. We will then use a similar model to determine the initial velocity of a spaceship flying close to the black hole. We found that the mass of the black hole is 1.778 times 10 to the 34 kilograms, and the initial velocity of the spaceship is negative 5.7 times 10 to the 7th, 3.2 times 10 to the 6th, and 0 meters per second. Concepts used in this lab are Newton's second law, parallel and perpendicular force, and gravitational force. These are some of the formulas used throughout the lab. These are the formulas relating to parallel and perpendicular force. We will use all the mentioned formulas in our code for creating the black hole model. Here are the free model diagrams of our lab. In part 1, the system is the star and the surroundings are the black hole and the rest of space. In part 2, the system is the planet and spaceship while the surroundings are the black hole and the rest of space. In part 1 of the lab, we used the computational model to determine the mass of the black hole. Here are the initial values used in the code. This image of our code shows the formulas that we are using. This video shows the results of running the code. The data states that the net force is 8.26746 times 10 to the 28 newtons. The parallel net force is 3.52516 times 10 to the 27 newtons, and the perpendicular net force is 8.25796 times 10 to the 28 newtons. By taking the average of all the masses given at each iteration, we can also find the mass of the black hole, which is 1.778 times 10 to the 34 kilograms. As the model has the star in an elliptical orbit, there are positions in the orbit where the star is closer to the black hole compared to another position. As shown by the arrows in the model, the gravitational force is stronger when the star is closer to the black hole and weaker when the star is further. Since the parallel component is related to the change in speed, the speed is greater when the star is closer to the black hole. Possible errors in this part of the lab would be rounding errors, which would have affected our calculations for the mass of the black hole. In part 2 of the lab, we must determine the initial velocity of a spaceship so that it may travel close to the black hole while still being able to leave the system. Here are the initial values in our code, and here are the formulas used for this part of the lab. This video shows the results of running the code. As you can see, the spaceship travels close to the black hole, which changes its direction, and the spaceship proceeds to leave the system. Using trial and error, the speed of the x and y component of the spaceship were determined. Using those values, we can determine the initial velocity of the spaceship in this model, which is negative 5.7 times 10 to the 7, 3.2 times 10 to the 6, and 0 meters per second. The value seen in the initial velocity indicates that the spaceship is moving left and up. The spaceship can leave the system as its speed increases as the spaceship gets closer to the black hole. Possible errors in this part of the lab are rounding errors and incorrect calculation of the black hole's mass from part 1. The net force and its parallel and perpendicular components are different from the rate of change in momentum and its parallel and perpendicular components. This can be seen by these two formulas shown. To make the spaceship orbit the black hole instead of leaving the system, we need to change the initial velocity. To force the spaceship into orbit, the magnitude of the x component of the initial velocity must be smaller, and the magnitude of the y component must be greater than that shown in part 2. Through trial and error, we were able to determine a new initial velocity, which caused this spaceship to orbit around the black hole as seen in the image.